Bismillahirrahmanirrahim. In this lecture, we are going to talk about the time evolution of expectation values. We want to look here at a time dependence of expectation value of a linear operator. This operator A is a linear operator, and his expectation value can be written as in this form. This is the expectation value, and it can be written as in this form. This is psi bra and A operator is operating on psi ket, where the state psi ket has a property, it can be normalized. Now we're going to take the derivative of this equation, then d over dt, expectation value or average value can be differentiated in this way. First we take the derivative of this one bra, and then we take the derivative of psi ket, and then we take the derivative of this. Then we have a three terms. Two terms are arranged in this way, and the final term is this one. This is according to the 3.76 and 3.77, which I have explained already. Now just because and after solving this equation, we have this form 1 over iota h, and then average value psi t bra and ah minus ha psi t ket plus psi t bra partial a over partial t psi t ket. Now 1 over iota h, and then this a and h can be written as in these brackets, commuting brackets, because this can be expanded as ah minus ha, same, and psi t and bra and psi t ket can be normalized here. Now, from this equation, two important results can be achieved. First one is that partial a over partial t average or rate of change of expectation value of a is equal to these two terms, and this factor partial a over partial t is equal to 0. How? This explicitly does not depend on time. If it is independent of time, then it will be equal to the 0. Now we have the solution of the expectation value with respect to time. We have just this term. First we have two terms. These terms were equal to 0. Why? Because a does not depend explicitly on time, so it vanishes. Now the second term is also going to 0. How it can be possible? When a and h both are commuting each other, then the answer will be equal to 0. A observable and Hamiltonian observables, if both are going to 0, commuting each other, then the answer will be 0. Then we have d over dt, expectation value is equal to 0. Here we have commuting brackets, answer is 0. We have partial a over partial t, because a does not depend on time, then is equal to 0. Then we have expectation derivative of expectation value with respect to time is equal to 0. What it means? A average is constant. What was the A average? A average is anything, any observable. For example, it may be Hamiltonian total energy. It means average value of total energy is a constant of any system. It may be the momentum, linear momentum. Momentum is conserved. Momentum is also constant. Average value is change in average value is zero. And similarly, the angular momentum can be also average value of angular momentum can also be zero. This is also called the constant of the system. It means total energy of the system remains constant, total momentum remains conserved, total angular momentum remains conserved. Now, uh, we are going to expand this relation because in previous calculation we were using just A. A was any observable. Now our observable is, for example, the probability. Probability can be expanded in this way. The probability will be the psi ket and psi bra or psi mod square. The probability, if we take the derivative with first derivative of this and the second one this, and then you use the equations uh, just like time dependent Schrodinger wave equation, and then we have this form, and then we just cut the relation minus 1 over iota h rho t h. It means rather than writing any observable A, we are writing here the probability density rho. Rho is some observable here. Now, if we use this relation that was previously we done 3.88, here we were writing A average, and here we were writing A, and here we were writing A for any observable. But here, rather than writing the A observable, we have the probability observable, and here is also probability observable is a probability. The same as we have done previously, that if the probability is independent of time, does not depend on time, then average value it's zero. And if both these rho and h are commuting to each other, then we have also uh, answer is equal to 0. Then finally we will get d over dt rho t is equal to the 0. It means um, expectation value of probability with respect to time is equal to the 0. Here we just the explanation of these terms, that how they're going to be 0. We are taking the uh, rho t and h, and there is a psi a bra, and here is psi ket, and here is just like A. We were discussing about the A, but there is a probability. Just expand this and answer will be equal to 0. Answer will be equal to the 0, and this term is also 0. It means change in probability with respect to time is equal to 0, or you can say the probability is also conserved. The average value or expectation value of the probability with respect to time is equal to the 0.